Yeah. Hi everyone. Welcome to the day 3 of Mini-Astro-workshop series 2020. So hopefully you all found the technical talks, the first two talks on Python programming and Julia, and also a basic introduction to command line interface and bash scripting and Git. They're up on YouTube. So we did share a previous email which had all the appropriate links as to what's the YouTube playlist where you would find these recorded lectures, and even there's a GitHub page if you all haven't seen yet. So please to go through the entire email whenever you send it to you, because we are trying to include as much as information possible in that email. uh, so we have also linked the resources etc that you people can go through after the lecture, so that you can learn that topic particularly well. And we've also started putting out our emails so that you can email us if you have any doubts. So if you have any doubt regarding some topic, so please email that particular person. And the email is also present on the GitHub page. Uh, and with that, if you'll have it, so as I was discussing with Komal. So the way we go about with the Q&A of this particular talk is, supposing there's a pressing question which needs to be answered so that that person can actually understand the talk well. That question, I'll try to bring it up to Komal's attention, and she'll try to answer it. And apart from this, she has also put a 10 to 15 minutes break in between the two talks. Like she's basically talking about two topics, and after the first topic she is going to have a 10 to 15 minutes break wherein she'll try to answer all the questions that are present on the chat. So unfortunately I can't unmute all individually, but what I could do is during the 10-15 minutes Q&A, supposing you have a question, you can just put a thumbs up, and I can unmute you. Else you can just put your question in the chat. Like as the talk goes on, you can just keep putting those questions in the chat, and look at them. And Komal will also look at them during that 10-15 minutes break and even after the talk. So the questions can range from anything like related topic, or a bit about the career in astrodynamics, because I don't think a lot of people, I mean, I personally haven't met a lot of people who worked in astrodynamics, but still I do believe that's a very interesting topic. So please to put your questions related to career in astrodynamics or regarding the topic in the chat. Uh, and I guess with that small brief pre-intro, so today I would like to welcome our speaker, Komal Gupta. So she just recently completed her bachelor's uh, in electrical and electronics engineering and Master of Science in Physics from Kepler Goa campus. And she did her thesis, undergrad, a master's thesis at the University of New South Wales, Canberra, where she was actually working with machine learning and its application to heteroclinic connections between the Lagrangian points L1 and L2. If I understand it correctly, sorry. I mean, this is a new topic too, so I'm really looking forward to this talk. And apart from this, she has been like consistently using deep learning, neural networks, and machine learning in astronomy and astrophysics. Like she did also work at NCRA, National Center for Radio Astrophysics, TFR, on developing a C program to analyze the pulsar profiling, and also using that to deduce some physical process responsible for the emissions that you see from the pulsars. Apart from this, she has also worked on some interesting topics like with Spilani Kekebula campus. She has also tried to understand how the inner ear actually works, trying to model it using some nonlinear oscillators, RC circuit, and the inhomogeneous Poisson process. So basically, she was trying to, I think, model the how can you understand the functioning of inner ear. And she has also worked in data analysis applied to cosmic microwave background. And she used neural networks to classify the galaxies based on their morphology. Uh, and she has also worked on ELISA. I mean, as you can see, she has worked on so many topics in the past with so much variety. So I'm very happy to welcome her, and I'm very looking forward to this talk. And with that, Komal, I give the floor to you.
Thank you, Surendra, for the wonderful introduction. I'm very happy to be here. And with that, let's begin the first part of my talk, which will be the fundamentals of astrodynamics. Now, my main aim with this lecture, the whole 1 hour or whatever it's going to be, is to introduce you to two concepts which I came across over the past year while I was doing my master's thesis. First of which is astrodynamics, and the second one is the second part of my talk, which is space situational awareness, or SSA. Now, before we begin, as Surendra said, we are going to have a break between the two parts of my lecture. So if you have any questions, just shoot them and put them in the chat box, and so we will let me know if you have anything. Okay. So let's start with the definition of what astrodynamics is, or how it has been, defined over the years. So people often confuse astrodynamics for classical mechanics, or these are terms that are usually used in place of each other. So for example, classical mechanics called orbital dynamics or latitude dynamics, but all of these fields are related to astrodynamics in some way or the other, but they're not quite the right thing. So they don't exactly mean what I am going to discuss today. So classical mechanics, for example, basically covers the dynamical motions of celestial objects. For example, if you have, if you want to talk about the orbit of the moon around the Earth, or that of the Earth around the moon, that physics is classical mechanics. Orbital dynamics usually concerns itself with all orbiting bodies. So in general, all orbital bodies come under the purview of orbital mechanics. Attitude dynamics is also kind of a sibling field to these. It deals with orientation of objects in space. But astrodynamics is a mixture, or you can say it's specific things handpicked from each of these fields. And it's the study of the motion of man-made objects, specifically man-made objects in space, which are subject to both natural as well as artificially induced forces. Now, natural forces obviously include gravity. You can have perturbation forces like drag or solar radiation pressure. Artificially induced forces can be thrust produced by rockets and so on. So modern astrodynamics is a descendant of astronomy of the old times. And when I say modern astrodynamics, I mean astrodynamics that has been done since 1950s, which was the beginning of the space race when Russia first launched the Sputnik satellite. Now, it's very closely related to celestial and orbital dynamics. And yeah, exactly what it is what we're gonna find out today. So a bit of history before I go on to exactly what we're talking about. Astrodynamics started with two people who are mainly credited with the foundation of the field in early 17th century. Now, first of these two people were as contradictory in their personalities as anybody else. So the first one, which is in the image on the left, you can see that it's a monument dedicated to Tycho Brahe and Johannes Kepler, both of which are credited with the foundation of for laying the foundation of astrodynamics. Now, these people were fairly contradictory, like I mentioned, in personality. Tycho, on one hand, was noble, aristocratic Danish, not mathematician, but he was exceptional in mechanical ingenuity. And he was meticulous in the collection as well as recording, I should say, collection and recording of accurate data on the position of planets. So he was, I don't know if I should call him an engineer, but yeah. On the other hand, there was Kepler. Kepler was a mathematician, and due to his health, he was not fit for taking up. He couldn't take observations accurately, but he was gifted with the power of mathematics, and he had what it took to unlock the secrets hidden in Tycho's data. Now, once Tycho and Kepler were active during the 17th century, another figure during the same time was Newton, who was a student at the University of Cambridge when an outbreak of the plague, which is not much unlike the pandemic that we're seeing today, forced his university to close down for some time. Now, that period was one of the most productive times in Newton's life, and in the long vacation of 1666, he conceived the law of gravitation, he conceived the laws of motion, and he also developed the fundamental concepts of differential calculus in 1666. But due to some inconsistencies in his mathematics, he set them aside. And it wasn't until 1685 when Halley, which is the same Halley as the person who discovered Halley's Comet, he encouraged Newton to publish his explanations of planetary motion. And it finally appeared in 1687 as the Principia, or the Mathematical Principles of Natural Philosophy in English. Now, what are the basic principles that these people came up with? The rules of thumb that astrodynamics follow are first Newton's laws of motion, Newton's law of gravitation, which both appeared in the Principia in 1687. Then there are Kepler's laws of planetary motion. Now, Kepler's laws appeared in 1609, which was before Newton came up with his laws, and Kepler's laws were only a description based on Tycho's observational data. Kepler found that he could fit an ellipse to the observational data, and by fitting that ellipse, he could come up with his laws of planetary motion in 1609. So the first two laws, which were published in 1609, say that the first law is that the orbit of each planet, it has to be an ellipse, and the sun has to be at one of the foci. The second law says the line joining the planet to the sun sweeps out equal areas in equal time. I'm sure everybody who has done classical mechanics remembers these. The third law came after a decade later, in 1619, and it says that the square of the period of a planet is proportional to the cube of its mean distance from the sun, which is also something we have all done in classical mechanics, or at least I hope so. So yeah, on the right, there's a handy diagram to mention that. So you can see that there are two ellipses, both of which have one focus at F1, which is the sun. The two ellipses refer to orbits of two planets. One of those ellipses you can see that there's a line that sweeps out an area A1 and another area A2. And we know that since if these areas are equal, then we can say that it took the planet equal amount of time to sweep these two areas, and that is the second law. First law is that the sun is at the focus. The third law is that if the ratio of semi-major axes of these two is A1 is to A2, then the period would be the square of the period would be proportional to the cube of that ratio. So yeah, the square of the ratio of periods would be proportional to the cube of the semi-major axis ratio. Okay, so mathematically, if we want to define orbits, and I promise you this is the first and the last slide that has some equations, some weird looking equations on my in my presentation. So mathematically, if we want to define orbits, we have to consider two body motion, which is two bodies moving under each other's mutual gravitation. The equations of motion can be written by using simply Newton's laws of gravitation, which is the first equation that we have here. And this equation can be solved analytically. And the solution is also mentioned here. Here, H is the angular moment, specific angular momentum, which is angular momentum divided by the total mass of the, or reduced mass of the system. B is a constant of integration, and V or nu is a parameter that tells you where along the orbit the satellite or the object actually is. But the thing to notice here, and the thing that is actually pretty interesting, is that it looks deceptively similar to that of this equation itself looks similar to that of the general equation of a conic section, which is written in a coordinate system such that the focus is at the origin is at the focus. This is basically telling you that all orbits in two-body systems are conic sections. Now, before we move on, one thing that we need to remember is the constants of motion, which I'm sure your physics instructors have in full or stressed multiple times. So the two constants of motion in this system are total mechanical energy and angular momentum. And the way to think why these, or the intuitive explanation behind why these two quantities are constants of motion is this. Let's say the gravitational field, we know that it's a conservative field. Therefore, anything moving under the effect of gravity should not lose or gain energy, right? I mean, that's what conservative field means. Now, it simply exchanges one form of energy for another, which means that the total mechanical energy will be a constant of motion. Similarly, you can think about angular momentum being a constant of motion, because to change the angular momentum, we need a force that is tangential to the direction of motion. But we need a force that is tangential to the system, to the object which is rotating. But here, the only force acting is gravity, which is always radial. So angular momentum is also a constant of motion. Now, I hope that makes sense. If you have any questions, then let me know. Now I can move on to geometry of an orbit. Now, orbits, you all must have heard of like elliptical orbits and parabolic orbits, hyperbolic orbits. These orbits differ from each other in terms of their energy. And geometrically, they differ from each other in terms of their eccentricity, but that is dependent on their energy. And there are some formulas here, but let's ignore that for the moment. So the geometry of an orbit depends, but the summary, the thing that these formulas mean is that the geometry of an orbit depends entirely on its energy. On its energy. So for elliptical orbits, we have eccentricity between 0 and 1 and energy less than 0, which is something you can verify by just these two formulas. Circular orbits are just a special case of elliptical orbits, not really found in nature, but some planets have orbits which have very low eccentricity, so they approximate a circle. Now, parabolic orbits will have eccentricity equal to 1, energy equal to 0, total energy equal to 0, which is again something that is not quite common in nature. Hyperbolic orbits have an eccentricity of greater than 1, energy also greater than 1, and these are orbits of most interstellar objects. So for example, there was an interstellar object that came to our solar system a couple of years ago, I think 2017, and that its orbit was hyperbolic. And most interplanetary probes sent from the Earth are sent on hyperbolic trajectories. So that's all about relations between energy and eccentricity. Now on to more practical things, such as how do we describe an orbit and how do we define an orbit uniquely? So this is done by using orbital elements. These are 6 elements that will uniquely determine your orbit. There's also a seventh component, which is the epoch at which these elements are defined, and that is basically the time at which these elements are defined. So there are 2 elements here, semi-major axes and eccentricity, that basically define the size and shape of the orbit itself. So these are parameters that come from an ellipse, and they give the size and shape of the ellipse. There are 2 elements that define the plane in which the orbit is in, which are inclination and longitude of ascending node. There is 1 element that defines the orientation of the orbit, which is argument of periapsis, and there is 1 element that defines once you have the orbit defined in your 3D space or 3D frame of reference, whatever it is that you're using, there is 1 element, which is the true anomaly, which tells you where exactly on the orbit is your element. Now, semi-major axes and eccentricity are fairly intuitive. I mean, they come directly from geometry. Inclination is simply the angle at which the angle between orbital plane and the plane of reference. Longitude of ascending node is the angle from the reference direction, which is usually taken to be the vernal equinox. So angle from the vernal equinox of the point where the orbital plane or of the line where the orbital plane intersects the plane of reference. And argument of periapsis is the periapsis angle. So angle from the line of nodes, which is this line, and from the line to the periapsis. And true anomaly is simply an angle between the periapsis and the location of the r vector, radius vector of the object. Now you can see that all of these orbits, all of these angles are not defined in the same plane, and one angle is defined in the plane of reference, one angle inclination is defined in the plane perpendicular to the plane of reference, the other angle is defined in the plane of the orbit. But this is not something we'll worry about right now. What we need to know is that there are 2 types of elements, or these are the 6 orbital elements, but they are basically defined in 2 separate sets. So there are oscillating elements, which are just Keplerian elements, these orbital elements, without considering perturbations from any other body. So, and by any other body, I mean, if we're talking about the sun, if we're talking about a satellite around the Earth, we mean for a perturbing body could be the moon, it could be the sun, it could be the largest planet, Jupiter. So when orbital elements are used or are calculated without taking the perturbing object into consideration, they are called oscillating elements. But these are not quite accurate, because in real life, we do have these objects that are perturbing our orbit. So we define mean elements, and mean elements define a general orbit or approximate orbit with some degree of accuracy over a given period of time. So mean elements are the ones that we would usually mean when we say, when we're looking at an ephemeris or something like that. And oscillating elements are only true for the time at which they're defined. Okay, so next step is, this is one way of characterizing orbits, which is based on their size, shape, inclination, and stuff like that. The other way we can characterize, or let's just say, the other way we can divide our orbits into types is based on their altitude from the surface of the Earth. So this handy diagram that I found on Wikipedia has several orbits from low Earth orbit to high Earth geostationary orbits. And these are different orbits that are different bands, as you can probably see here. There's a low band close to the Earth, and there's a band around 20,000 to 25,000 kilometers. And there's a band at the end of the and outermost band here. So these are basically orbits defined, divided into classes based on their altitude. And each of these orbits has a specific purpose. Now, before I move on, I just want to say this diagram might be a bit misleading, because here we're looking at the Earth from the North Pole. So we're at a point that is above the North Pole. And it may seem that all of these orbits are placed nicely in a plane around the Earth, but that is not quite true. So let's just ignore that for a moment, and let's just look at the altitudes here to define the different regions where that the orbits may occupy. I mean, the orbits can occupy any region, but yeah, different bands that are defined around the Earth to classify the orbits into different sections, different classes. So let's just move from the inside to out. Low Earth orbits are the orbits that are closest to the Earth. So here in this diagram, they go from, I think, go up to 800 kilometers or so in altitude, height above sea level. And these are orbits that are occupied by communication satellites. They have science and weather satellites, satellites that have that observe the Earth, so terrestrial observation satellites. They also have, this orbit is also used by ISS and Hubble. There are also a particular type of or class of orbit that are perpendicular to this plane that we're looking at. And those are called polar orbits, and they have their own purpose. But if let's just focus on this region for a moment. Now, this is, as you can see, this plays inside or below the inner Van Allen belt, because obviously we can't put anything inside the Van Allen belts. Then coming towards further away from the surface of the Earth, we see another band, which is the medium Earth orbit. Now, these usually contain navigational satellites and navigational and satellites that have to, some satellites that have extremely high eccentricity and are made to orbit, made for observation of high latitudes. And even further, we have high Earth orbit, which is commonly known as just geostationary orbit. This orbit is useful because the period here is the same as the Earth's period of rotation, which is 24 hours. So the satellite, in any satellite or any object in this orbit, appears to stay at the same position compared to an observer on the ground. And most geostationary satellites are for weather monitoring, for communication, and also for monitoring space weather, so solar activity and space weather. So these are the three or loosely defined 3 main bands in which we put our satellites, and there are obviously tons of other satellites that move in and out based on their eccentricity. I think this would be the right time to show you this interesting visualization, which is a simulation of all the objects, or not all, but yeah, most of the objects that surround the Earth. So yeah, here, this is the view. This view from the North Pole is what we have in the diagram on the presentation. And here you can clearly see that there's a ring of geostationary satellites, all of which have a period of 24 hours because of their altitude. And I think I should have mentioned this before, but as you move away from the surface of the Earth, the period, if you have a circular orbit, the period of the satellite, period of the orbit will increase. So the orbits in the low Earth orbit, so the satellites in the low Earth orbit, which seems pretty crowded here, and it is, and we'll come to that later. These have periods ranging from a few hours to maybe a couple of hours, and then we go further and further away, and the period increases, and finally we get to the geostationary ring, which has a period of exactly 24 hours, and it's useful for weather monitoring and communication, stuff like that. So as you can see, each orbit has a dedicated purpose, and if we want to, and it depends on what the type of orbit depends on the satellite's mission, and it's very important that we make note of where we want to put our satellite, and that is based on what we want to achieve with it. I think you can also see a band of satellites here, approximately, which is the medium Earth orbit, and which is where GPS satellites and Galileo and the other navigation satellites are into. Yeah, I'm not sure if you can see it, but yeah, there's a faint band here, which has the navigation satellites, and the geostationary ring is pretty prominent here. Okay, so how do we get to the orbit? And that we all know that's achieved by means of rockets, and how much energy is required to place that satellite in its orbit depends on the location of the launch site. It also depends on the altitude and the inclination of the desired orbit. High orbits require a lot more energy than low Earth orbits, because you're trying to put your satellite further away from the Earth, and that will take more energy because you're trying to get further and further away from the Earth's gravitational effect, gravitational well. So the amount of energy also depends on the location of the launch site, which is why most launch sites are placed close to the equator. A satellite with low inclination, or an orbit with low inclination, I should say, it can use to place a satellite into low inclination orbit. We can use the Earth's rotation to pump some extra energy, and for that reason, polar orbits would usually require more energy than orbits of less inclination. But in general, the amount of energy required to place an orbit is a fairly straightforward calculation. In addition, transfer orbits are often used to move satellites from one orbit to another, and that is something that we are not going to discuss today. The next thing is maintaining orbit. How do we, once we get to the orbit, how do we stay there? And that is a problem, often because there are perturbations, like I mentioned before, and these perturbations change the orbital elements over time. And this not only do these perturbations include third third body perturbations, such as gravitational effects from Sun and Jupiter and other planets of the solar system. They also include gravitational effects due to the non-spherical and inhomogeneous nature of the Earth. They all include, there are perturbations due to atmospheric drag, which is specifically, which is more important for low Earth orbits than it is for high Earth orbits, where the atmosphere is thinner. The perturbations are also caused by solar radiation pressure, which slowly change the orbital elements of the satellite. And if it is to stay in a particular orbit, then the satellite will have to use what are known as station keeping maneuvers to basically turn its thrusters on and correct its position to stay in a particular orbit. Moreover, satellites may also have to move due to collision with space debris, which is something that we will cover in the second part of my talk. A very important part of astrodynamics is determining the orbit and predicting the orbit, which is commonly known as orbit determination and prediction. Orbit determination basically deals with predicting or finding the radius and velocity vector of an object in orbit. Now, knowing the position and velocity is especially important for terrestrial observations. It's also important for meteorological satellites, and yeah, so it's important, and it's also important for collision avoidance and other things which we'll cover in the second part. Now, observations are usually taken from ground stations, and these ground stations, such as the one on the left side, these ground stations are basically based on radar, or they might also have some optical telescope equipment. These observations, and now we have come a long way from the time of Kepler, who used curve fitting to determine the orbit. So now since we have the equipment and the theoretical knowledge to do so, we can use several different algorithms to determine the orbit of a satellite with precision. For example, the only two observations of a satellite is required, and by two observations I mean with every observation we can find the position vector and the velocity vector with some with only two observations. I mean, with the observations, it can be position of velocity vector if we're using radar, or it can be the angles on azimuthal and altitude angle, or you can have RA deck angles. So two such observations are required if we are to use a method known as Lambert's method, which has been around for quite some time. Then there's another method which was used by Gauss in 1801 to recover a lost minor planet. Now, you can ask me, how do you lose a minor planet? I mean, yeah, you just, if you saw it once and you can't see it again, then you've lost it. So in 1801, Gauss used his method to recover the position of the minor planet known as Sirius. And this method uses 3 or more observations of right ascension and declination angles of the satellite. And using this, we can find the position and velocity vector accurately. In addition, we can find the orbit. In addition to just the observations, we can use the equations of motion that describe the forces on the spacecraft, as well as the relationship between the parameters and the satellite's state vector, which is basically the frame that we are observing it in, and relative to an inertial frame. We can use and then we can use a least squares type of algorithm to to determine the orbit with precision. Here, I have a diagram which basically tells you how orbit determination and orbit prediction is usually carried out. Orbit prediction is trying to find trying to predict the orbital state vectors of a satellite at any point in the future based on the observations that we have so far. And because of the proliferation of space objects, especially during the recent years, we cannot actually track each and every object at all times. So we need orbit prediction to predict the orbit for us so that we don't need to track it all the time, and we can just look at it, store its position and velocity, and then the next time if we want to find it, we know where to look. Now, orbit prediction algorithms range from analytical to numerical algorithms. They have their own different metrics for speed and accuracy. There are also semi-analytical methods that are becoming very popular these days. Yeah, and in this diagram, you can see that it basically tells you the relationship between orbit determination and orbit prediction and how it's carried out. So initially, a ground station observes the satellite, and it takes multiple observations of the satellite and the time at which it observed it. It goes through an initial orbit determination algorithm. That orbit determination algorithm gives you an initial set of radius and velocity vectors. Now, by using an iterative process known as differential correction, you can basically use subsequent observations of the satellite to correct your orbit. So, which means we can, with a small number of observations, we can get the radius and velocity vectors with some accuracy. But with additional observations, we can fine tune them, and we can use differential correction process to get closer and closer to the correct values of radius and velocity vectors. And then these values are propagated in time. That generates an ephemeris, which is used for everything from close up analysis of close approaches, therefore rise set times, used for station keeping maneuvers, and it's used for multiple reasons in different space missions. And these ephemeris also tells you where to look for the same object if you want to find it sometime in the future. And that's how it's done. And a very important thing, in a very important part of orbit prediction, is two-line elements. So two-line elements are a way of encoding information about orbits, and they're called two-line elements for the very reason that they can be written in two lines, even though there is a third line which mentions the name of the satellite. So yeah, two-line elements have been used for quite some time. They're used only for Earth orbiting objects, and they are released and updated frequently by organizations like NORAD and NASA. They can only be used by a particular model, which you can think of as an integrator, which takes these elements, takes the time at which these elements were defined, and takes a future or a time value in the future as inputs, and it gives you the two-line element at that future time value. So it can give you the value of, so the model basically propagates the TLEs along in time, and it can give you it can predict the orbit for you at any time in the future. Not at any time, because these TLEs are only valid for a particular duration, and that depends on when they were released and what was the accuracy with which these values were release. So orbit determination and prediction is a very important part of astrodynamics, and a lot of research has been going on into how to make these algorithms better. My own thesis started with trying to predict orbits based on using machine learning, but then we moved on in a different direction, and yeah, never could get back to that. So yeah, so that's so orbit determination is also very important. Determination as well as prediction, I should say, is a very important part for what we will discuss later, which is space situational awareness, or SSA. But for now, let's just have a brief break for 5 or 10 minutes. And if you have any questions, I can take them. And if not, then we can move on.
Hi, Komal. So people did put up questions in the chat. So do you want me to read them or you want to look at them?
Okay, yeah, I can look at them. Can
so
you,
what you
okay,
can do is you can call out the name and the question.
Right. So Sayam is asking, can you please explain the Van Allen belt? Yeah, sure. So the Van Allen belt is basically an area where a region in space where how should I put it? There's a large concentration of charged particles. So it interferes with the satellites, and that is why we cannot. It interferes with the communication, and it might even it's bad for the circuits in the satellite. So it's not ideal to put any object inside the Van Allen belt. That's why the low Earth orbit kind of ends at the inner Van Allen belt. There's another Van Allen belt, which is the outer Van Allen belt. And here again, you can see there's a gap between medium and high Earth orbits. So yeah, these regions are like a no-go zone in space, and we cannot put satellites in here. If you wanna, even in this diagram, I think you can see that there's kind of a gap between the outermost circle and the mid circle is here, where medium Earth orbits, and then there's another gap between the medium Earth orbit and the low Earth orbits. So these, because of the high concentration of charged particles, these Van Allen belts cannot harbor satellites, and that's why they're not useful to us for putting on satellites. Okay, I hope that answers your question, Sayam. Okay, great. From Soham Mitra, how is the vernal equinox position determined for different celestial body systems like Earth and a satellite or moon during a specific epoch? And do they have any relation with the vernal equinox position of the Earth? Right. So vernal equinox is a direction that is defined along the Earth's orbit. So I shouldn't put it say along the Earth's orbit, but it's a direction in space that points towards the constellation Aries, and yeah, it's a fixed direction. It's also the angle. It's also the line that is. I don't think I can link. I think this diagram would help. It's the line that let's just, can I draw in this? How do I draw here? Wait, no. Yes.
So if you actually go to your screen sharing,
yeah,
you can actually annotate. I think, yeah.
Okay, yeah, I think this should work. So let's say you have the ecliptic, which is the plane in which the sun appears to move with respect to the Earth. You also have the equator of the Earth, the celestial equator, the equator of the Earth projected onto the celestial sphere. This here is the Earth Sorry for the bad diagram, but the vernal equinox is basically just a direction that is defined as a reference in the three-dimensional space. And how is it determined for different celestial body systems like Earth and satellite or Moon, and the satellite during a specific epoch? I'm not sure I understand the rest of this question. Soham, would you like to just explain what you mean to me right now? Can you hear me? Hello?
Can you hear me?
So Hamitra, I've unmuted you. You can ask your question.
Hello?
Yeah.
My question was like, when like for different, like you explain the orbital elements for a satellite in this diagram. So I'm asking, like, if there is a satellite around moon, for example, then how the orbital elements for that satellite will be determined around moon? Like
so yeah, the vernal equinox is just a general reference direction in the Earth's frame. So in a frame that is fixed on the Earth, right? So if you go to the moon, you will take something else as the reference direction. It could be parallel to the vernal equinox. It could be something else. But again, you will need a reference direction to define longitude of ascending node and other angles. So yeah, it might be vernal equinox. I'm not sure what it is, but this reference direction is the vernal equinox when we're talking about orbits around the Earth. Does that make sense? Okay, great. Okay, next question is, can the orbit of a satellite be made 24 hours at any distance away by increasing or decreasing its energy? So now Dwich is asked, I hope I understand your question correctly. You're saying the orbit of a satellite be made 24 hours at any distance away from the Earth. Yeah, so the orbit of the satellite is 24 hours for the geostationary ring. So every satellite in the geostationary ring orbits the Earth in about 24 hours. So yeah, and by increasing or decreasing its energy, well, the energy will be higher for as you go further and further away. But yeah, the orbit is the period is 24 hours for satellites in the geostationary ring, as well as other satellites. They're specifically called geo or geosynchronous or geostationary satellites. And their particular, the reason why they're useful is because their period is 24 hours. Does that make sense? Dwight?
I think Komal, he's trying to ask whether this geostationary orbit can actually occur at other radii apart from different.
Oh, yeah. Right. Okay, no, that's not possible, because the orbital period is dependent on the radius of the orbit. Because yeah, so I get it now. Yeah, the orbital period is dependent on the radius of the orbit. So no, these satellites will have their own period, and you can't change the period and not change the altitude, or you cannot change the altitude and not change the period. Okay, so this orbit, this is a sweet spot when it comes to altitudes, and yeah, when you put something here, yeah, sorry, what if we increase its kinetic energy externally? By externally, do you mean using propulsion? Yeah, I hope that's what it is. So increasing its kinetic energy does not exactly translate to, or does not exactly translate only to changing the height. There are these orbital elements, all 6 of them will change if depending on where you, where your, or how much energy you have. So if you do, I don't think that is possible to increase its kinetic energy. And yeah. So that is correct. If you decrease the energy or if you increase the energy, the altitude will also change, and hence the period will also change. So hence the sweet spot. So that this ring itself has a particular energy which makes it right for, which makes its orbital period 24 hours. So does that make sense? Okay. Great. Any other questions?
Yeah, so there's one more question from Luke. If you go up below, he asks, can you predict seasonal changes because of the sun in Earth using astrodynamics? For example, if we consider the local equatorial coordinate system, then sun orbits around the Earth. So can we predict the position of vernal equinox?
So the vernal equinox is a fixed position, fixed direction in space. It's a reference direction. It's a line that we'll use as a reference to define our orbits when we're talking about orbital elements. So I am not sure how this would work, because predicting seasonal changes means seasons are because of the Earth's position in its orbit, and astrodynamics is not quite, not exactly that. So yeah, I'm not sure I understand what you're trying to ask.
Please, I've asked you to unmute. You can unmute yourself and ask the question.
Yeah. So actually, I was asking that when you have a local equatorial system, then you know that the sun moves around the center of the Earth. So
Yeah.
So we can know the orbit of the sun, right? Using astrodynamics,
Yes.
and then we can understand the seasonal changes accurately. That's what the question was. So can we do that using astrodynamics?
Using astrodynamics, you can predict positions of objects. You can come up with where they are, where they would be. So if that does that translate to seasons? I don't know, honestly, and I don't think so. I don't think that part is what astrodynamics concerns itself with. But yeah, I don't know how that would work.
Yeah, maybe
Yeah.
let's just keep that question for another time. I think basically he's trying to ask if we know the position accurately, like maybe like even the sun affects the seasons, right? Somehow. So I think the question comes from that way of thinking. But then,
Yeah, I think indirectly, if you think about it, if you know the sun's position in space, you also know when it'll rise, when it'll set, and that can tell you what part of the year you're in. And by guessing what part of the year you're in and which hemisphere you're in, you can tell what season you're in. So that way, this might work.
yeah. So Komal, I have a question of my own. So I wanted to know what accuracy in terms of order do you need this data for actually a good predictions, and also do the current observations actually cater to that?
Yeah, so no, because even the thing is, every orbit, it's different for each orbit. So if you have a low, if you're in low Earth orbit, it's easier to get more accurate observations, because the radar or the pulses itself has to travel less distance through the atmosphere, so there's less attrition in that sense. But if you're in a high Earth orbit, it's more difficult to gather more accurate observations. That's why, but instead of using just one observation or just two observations, there are hundreds and 200s and 300s of, or 300 of observations used, and each observation is taken at a different time, and they all contribute to slowly decreasing the error in the position and velocity vectors that we want. So I'm not sure exactly what magnitude it is. I think it's in position. I think it's of the order of centimeters, the error. And but yeah, that's just a guess. Something I remember. I'm not sure of the exact values, but I think in position it's of the order of centimeters, and in velocity it's of the order of some millimeters per second, something.
Okay. I mean, I was curious about this because you were saying that one of the sources of perturbations can actually be the solar radiation. So
yes,
actually
solar radiation pressure
factor.
Sorry?
Is it actually a very important factor, solar radiation, perturbing the orbits?
Yes.
Or? Okay.
Yeah. So solar radiation pressure is a factor because satellites have solar panels designed specifically to, collect solar radiation and then convert it into energy. But I'm not sure how, what factor of the total perturbation comes from solar radiation pressure. Other perturbations, like, for example, atmospheric drag, depends on how far away, or depends on the altitude of the Earth, altitude of the satellite, my bad, altitude of the satellite. So for low Earth orbits, the drag will be more than for high Earth orbits. Solar radiation pressure is also a factor, and it also depends on whether the satellite is in between, like whether the rays of the sun are falling into it, or whether it's in the shadow. So yeah, these things also change the magnitude during the day. Yeah, I read somewhere, so Sayam is saying, I read somewhere that if it weren't for the magnetic field of the Earth, the solar storms could have destroyed the planet easily. Yeah, Sayam, so yeah, you're right. The magnetic field does protect us against harmful charged particles that are coming from the Earth, and it helps communication, and yeah, so prevents communication blackouts and keeps our satellites healthy and safe. But the question that Surendra was trying to ask is how important is solar radiation pressure compared to other perturbations? I think that's what it was, right, Surendra?
Yeah, that's it.
Yeah, so solar radiation, it's not just the flux that the Earth receives. It's more of how much force is because of that solar radiation pressure on the solar panels of the satellite, and how much does it affect the orbital elements. So yeah, it is important. It also changes. It's also something that changes during the day. So when the satellite is in the shadow of the Earth, it's different. When it's between the sun and the Earth, then it's different. In addition, there is also pressure due to the light that is reflected off the Earth. So when a satellite is on the day side of the Earth, there is light that is reflected from the Earth to the satellite. There's radiation pressure due to that as well. Indirectly, there is pressure because of that as well. So there are lots of perturbations that change orbital elements, and that's why satellites need to have thrusters and do maneuvers. So Nitish is asking, up to what factor magnetic field change the orbit of a satellite? Is it low or high? Well, yeah, magnetic field does affect the satellite, and it's often included in the model itself. So in the orbit determination models, we include gravity, we include perturbation models. We also include Lorentz force, which is the force due to the magnetic field. So yeah, it is a significant factor. I'm not sure what order it is in compared to gravity and SRP, but yeah, it's definitely something that cannot be ignored. And once again, it's something that depends on where the satellite is actually. So depending on if it's in low Earth, medium, or high Earth orbits. Yeah. Okay.
I guess we'll stop here, in the sense like we'll stop with the Q&A and we'll take more questions at the end of the talk.
Okay, great. So yeah, let's move on. The next part of my talk is about space situational awareness, and which is something I don't know if many people have come across this term recently, but it's becoming a more and more important part of space operations. And so first, let's start by defining what space situational awareness, or SSA, actually is. Let me just close this box. Yeah. So space situational awareness refers to our knowledge of the space environment around us. And the goal of SSA is to detect, it's to predict, assess, and mitigate the threat to life and property, both life and property, both on ground and in space, due to natural or man-made orbital debris, as well as due to space weather. And by space weather, I mean solar wind, magnetosphere, ionosphere, thermosphere, anything that can affect spaceborne or ground-based infrastructure. So according to ESA, that's the European Space Agency, there are 3 segments that SSA is divided into. The first is space surveillance and tracking, which basically concerns itself with tracking the objects in Earth's orbit and keeping track of all the active and inactive satellites, discarded launch stages, fragmentation debris, anything else that we have left up there. Space weather, like I just mentioned, solar wind, magnetosphere, ionosphere, thermosphere, anything that can affect any amount of any condition that can, any weather condition, you can call it weather, that can affect our assets in space or on the ground. And the third branch is that of near Earth orbit objects, which are natural objects that can potentially cause damage to either the Earth or something that's orbiting the Earth. And the largest part by far is the space surveillance and tracking part that aims to create a catalog of all the objects around the Earth. This catalog forms the basis of orbital evolution and conjunction assessment, both of which I'll mention what they are later. And the conjunction assessment is basically something that aims to assess the risk of collision with debris, and it aims to protect our assets from collision. And the second most important part is space weather, which is obviously always changing, just like we just discussed a few minutes ago, that space weather, including conditions in the sun, or solar flares, and magnetosphere, these things can affect active satellite and cause damage. The third part is probably the least significant, or maybe not significant, but least scary part, is the natural space debris, which is asteroids, meteors that routinely pass near the Earth and threaten to collide with one of our satellites or something. These things cause often break space shuttle windows, but that's still lower on the threat list when compared to orbital debris or man-made orbital debris and space weather. So just yeah. So the SSA is divided into different components, like I just mentioned: space weather, orbiting space debris, natural space debris. Orbiting space objects includes both active and artificial, active satellites and artificial space debris. Artificial space debris would also include inactive satellites or anything that we have left up there, even hardware that maybe flew away from somebody on the ISS or something like that. So all of these things constitute space debris, and or the tracking part aims to keep a catalog of these things. Space weather part concerns itself with the electromagnetic radiation, subatomic particles, solar radiation, or particles that come from the sun. And then natural space debris is obviously meteoroids, asteroid, comet, anything that is not man-made and is not natural and may pose a threat. Now, why is SSA important? Well, we have been pretty dependent on space objects. If you look around you, GPS, weather, these things are dependent on satellites. And so we are indirectly, and we are fairly dependent on space objects for navigation and weather and Earth observation. And space has become a critical infrastructure for in our day-to-day life. And that doesn't just end there. I mean, we also have human outposts in space, such as the ISS, and these things are an asset, not just to any particular group of people, but rather for humanity as a whole. And that makes tracking and cataloging objects even more important for not just scientific purposes, but also for collision avoidance purposes, and for collision avoidance purposes, so that we can protect life as well as property in space, as well as on the ground. And in recent years, SSA has become more important because since the beginning, I'm just gonna present some numbers now. So since the beginning of the space race, which was when Russia launched Sputnik, there have been more than 5,000 space missions worldwide, and out of the 40,000 objects that have been catalogued by the US Space Surveillance Network, or SSN, for 17,000, more than 17,000, are still in orbit and are traveling independently. And this is data from NASA, taken from one of their quarterly reports in one, and it concerns its information up to so from the beginning of the space race up to 1st of January 2016. So if you just look at this diagram here, it tells you how many objects are there in each orbit, and it doesn't go beyond LEO, so it only ends at 2,000 kilometers. And you can see that the red ones are the ones that we can track right now with our radars and our ground stations and everything. And the orange one is the one, the orange line is the one that will be tracked. We expect them to be tracked with space fence, which is kind of like a second generation space tracking infrastructure. And the blue line, which is far beyond either of these two, is the amount is the potentially lethal debris or objects that we have orbiting the Earth. So you can see that the need, it's very important that we know where these are, where we know our space environment, and that we know where each of these objects are, and so that we can plan in advance, and we can protect our assets in space. And I would like to get your attention back to this diagram, this visualization, which now from the perspective of SSA, you can see that there is a ton is probably an understatement, but you can see that there is quite a lot of stuff out here. And here the red objects are the satellites, the blue objects are the rocket bodies, and there are quite a lot of those blue objects. The red ones are active satellites. The blue ones are rocket bodies, which are basically a huge part of, make up a huge part of space debris. And if we come to Leo, you see that the situation only gets worse, and there is a lot of these gray specks, which are debris objects. Now, it is in general, it is accepted that any collision with an object that is greater than 1 centimeters across will be potentially lethal to the satellite's mission. And if we just look at this, so we'll come back to that later. But if we just look at this diagram, we can see that since the beginning of the space race, it has only the number of, not just the total number of objects, but also the debris as well as rocket bodies and everything else has only gone up. It's not slowing down, and if anything, it's increasing it's going up at an increasing pace. Two of these events, such as destruction of a Chinese satellite by in an anti-satellite test, and the collision between Iridium and Cosmos satellites, have increased the number of debris by a huge amount. So these things only enforce the need for a good space surveillance system or a good SSA infrastructure that can do all the things that I mentioned above. Another such visualization is this one, which shows you the number of cataloged objects in Geo. Now, number of cataloged objects is there's a bit of a catch here, because the number of only objects that are greater than 10 centimeters across can be tracked by the system that we have right now. And if any object that is more than 1 centimeter across will be lethal. So you can see the problem here. Anything that is greater than 10 centimeters is lethal, but anything that is greater than 1 centimeter is lethal, but anything that is less than 10 centimeters cannot be tracked. So this just serves to reinforce the how should I put it? Reinforce the need for a good space situational awareness system that can track and that can catalog so many objects at the same time, and allow us to plan our missions, or plan our scientific missions in a way that is healthy for, should I say healthy, or in a way that it protects our assets. Now, so if you just if you're not convinced yet about the threat presented by orbital debris, yeah, there are some. These are some of the images I found somewhere hiding on the internet. These the first one and the third one here are both images of Hubble. I think this one is an antenna on the right, and the left one is a solar panel of the Hubble Space Telescope. And this shows the impact of collision with space debris. The image at the bottom is just, I'm not sure exactly what it is, but it's an object. It shows you how much of a damage something really small can do to a satellite, simply because it's moving at a very high speed. And yeah, and which is why it's extremely important that we make sure that we have plans in place to protect our assets against these debris. Now, I just wanted to mention some of the worst collisions in history. As you could probably see here, these two collisions increased the number of objects in orbit around the Earth by a huge margin. The first one was a Chinese anti-satellite missile test in 2007. I'm not sure if you can see this diagram. Let me just full screen my screen. Okay, yeah. So yeah, the first one is this Chinese anti-satellite missile test, and you can see the red dots are the number of debris that it, the debris objects that it created, and these are just the tracked debris. These are not, and like I said, anything below 10 centimeters cannot be tracked so far. So these are the debris that we can track. And mind you, this is a collision in the low Earth orbit. So it's happened in a region where the density of spacecrafts is already so high that makes this a very serious problem for future missions, as well as objects that are presently operating in the low Earth orbit. You can see the International Space Station's orbit here, and as a green line, and the other LEO objects are green dots. And by the way, at the time in 2007, this anti-satellite missile test it created more orbital debris than any other mission had before it. So it was the most serious collision, not an unintentional one. So it was the most serious event that created tons and tons of debris. This second one was an unintentional collision between a communication satellite owned by Iridium Corporation. It was an active satellite, and the other satellite was a Russian military satellite, Cosmos satellite, which was actually not functional at the time. And this collision happened nearly at right angles, and it destroyed both the satellites completely. The Iridium one, as I said, was active at the time, and it wasn't. They didn't realize until I think a couple of days ago. A couple of days after the collision, that one of their satellites have been lost due to this collision. You can see that the debris field increased very quickly, and it just shattered both of the satellites, and just ended. Just ended one active satellite and the other one, and other defunct one. And it is so far, this collision so far is the most severe accidental fragmentation on record. It's the one event that has created more orbital debris than anything else so far. And it's not that this is not to think that collisions are something that happens every once in a while, or despite having thousands and thousands of objects in the in orbit, these are not isolated incidents. For example, and this is not something that happens rarely. It's a very real concern. For example, recently in September 2019, I'm not sure if you guys followed the news at that time, but one of SpaceX's Starlink satellites had a significant risk of colliding with a European Space Agency satellite. And to prevent, because everything here is probabilistic, so we can only say that there's a fixed probability that something will collide with something else. In this case, the risk was quite high. So ESA had to maneuver its satellite out of the way because the Starlink one didn't have any propulsion. So it couldn't move out of the way, but ESA had to maneuver its satellite out of the way to prevent the collision, to reduce the probability of collision. During the same month, two large defunct satellites, and that is even bigger of a problem, because if both the satellites are defunct, that means neither of them can move out of the orbit and away from the collision. So all we can do is sit and watch. And those were Cosmos 1300 and Bigelow Genesis 2. They were assessed to be at a risk of more than 5% of colliding, which is a huge risk. 5% may not look like a lot, but was a big risk. But it didn't end up happening. But it still was something that concerned the SSA community for a long time. And even this year, there was concern about high risk of potential head-on collision between an infrared astronomical satellite and another gravity gradient experimentation satellite, which were both not operational and both were non-maneuverable. So again, the only thing that SSA community could do was to hope that it doesn't collide and to keep track of debris if it does. And it's and even this past week, I'm sure this made big waves in news. I'm sure you must have come across this if you follow the International Space Station on Twitter, or if you get some news about the International Space Station. This past week, I think September 22, ISS had to maneuver. They had to conduct a maneuver to move out of the way of a space debris object. And they did so. They conducted the maneuver, and they safely passed, and nothing really happened. But it's still these type of collisions. The threat of space debris is still very, very real, and it's very important that we do something. And it's high time that we start planning in a way that it's part of the satellite's operation itself. So collisions can be avoided, so it's not something that is completely out of our control. They can be avoided, and in fact, more and more satellite operators are putting collision avoidance as a part of their routine space operations. In general, debris avoidance maneuvers are planned when the probability of collision reaches about 1 in 100,000. So if the probability is greater than 1 in 100,000, a maneuver will be conducted. If it will not result in significant impact to mission objectives. And if it is greater than 1 in 10,000, a maneuver will be conducted unless it will result in additional risk to the crew itself. So collision avoidance is becoming a larger and larger part of the of space operations. I just want to briefly mention what the pipeline looks like. So the first part is to first identify conjunctions, and this word I have used a couple of times before. Conjunction is basically an event that where two satellites, or doesn't have to be two satellites, but an active satellite and or two tracked objects, let's just say, pass very close to each other. Such an event where they pass very close to each other and they are at a risk of colliding with each other, even if that risk might be minuscule, is known as this event is known as a conjunction. Now, conjunctions are usually determined by using orbit prediction that I mentioned before. So orbits are propagated into the future, and that's how we know if something is going to pass, if two things are at a risk of colliding. Now, if such a conjunction event is about to occur, there's a conjunction data message, or CDM for short, that is generated, which contains information about the conjunction itself. So for example, the probability of collision and the position and velocity of the two objects, the error in position and velocity, which is again a very important part. So these values are put in a conjunction data message, and it is released, and it is given over to the analysts who analyze these conjunction data messages, and they decide whether to maneuver the satellite out of the way, or whether there is a need for maneuver or not. And only if the risk of collision is high, the satellite is maneuvered out of the way. And yeah, that's how avoidance is performed currently. Okay, so that basically concludes everything that I have wanted to say about SSA. I just want to summarize what it means to have a sustainable space environment. Basically, we'll need to focus in the future, if we want to have a sustainable space environment in a way that is feasible without such a huge risk of space debris, of collisions with space debris. We will have to look at three main goals. So the first one is mitigation of debris, which basically intends to minimize the creation of future debris itself. And this is only a short-term solution, because we can prevent in-orbit, we can try to prevent in-orbit collisions, we can try to prevent explosions, and we can try yeah, these things can solve our problems for a short time only, because the debris that is already there is there. So we can't do anything about that, but we can reduce the risk of increasing that number again, like we did accidentally happened during the Iridium Cosmos collision and the Chinese anti-satellite test. The other way of debris mitigation could be post-mission disposal, which is also something that many operators plan as part of the mission. So if the satellite is in a geostationary orbit, there's another orbit which is designated as a graveyard orbit, where satellites are maneuvered at the end of their life. Satellites are maneuvered into that graveyard orbit, and they would stay there, and yeah, so stay there and not clog the important geostationary ring that we have, that we need. The other, you can call it medium-term solution, would be space traffic management, which is exactly what I mentioned earlier. That is tracking and cataloging all the objects that we have in our space environment, and using collision avoidance and maybe stuff like shielding our spacecraft, which is already done for a lot of missions, to protect our assets against debris, both natural and artificial. And finally, a long-term method, long-term solution would be to remove the already existing debris from orbit, which is something that has not received as much consideration so far, but it's something that is becoming more and more important in the future, because the first two methods only reduce the rise of or the sharp rise of debris, but this third method is this third line of thought is required to remove the already existing debris from orbit. And we can do it using a dedicated space mission, or we can come up with other ideas. I'm sure people have proposed different ideas. I've heard talks about using lasers to push debris out of orbit. But yeah, this is something that has not received as much consideration. So yeah, that's all. If you want to read about these things further, you can refer to one of these resources. I'll put the slides on the internet, so yeah, these will be available and you can go through them later. That is all. Now, if you guys have any questions, let's just discuss. I would love to talk to you now in general, like without being just constrained by the presentation. So yeah, anything that anybody wants to point out?
Yes, so I do have a lot of questions to ask, but I'll keep them towards the end.
Yeah.
So if participants, if you all have any questions, now is the time. You can put them in the chat. And also, if you want to ask by talking, you can just say yes. You can click on yes and I'll unmute you all. So
Surendra, I see Dwej is asking, can such problem be stopped? But I don't know what problem he's referring to. So Dwej, what part of the presentation do you mean? Space debris be stopped, or do you mean collision?
Yeah, the space debris thing. So you said one of the problems could be solved using lasers, right? But that would be extremely costly.
Yeah, exactly. So these are only things that are hypothetical at this point, and we need people to brainstorm ideas and think about things, ways to remove already existing debris. And right now, the most feasible one, the most feasible one of, the most feasible one that we can think of right now is to use a dedicated vehicle to collect space debris, and even that is fairly expensive for each. And there are hundreds and thousands of space debris objects that have to be removed. So it is the financial side of it does not look very good right now. But yeah, it's something that people have started to think about now, because the first two of these can only take us so far. For sustainability of space, we need a long-term method, and this debris removal is the only is a long-term method.
okay, yeah. So as I was saying, you can either put a yes, you can click on yes and I'll unmute you all if you have any questions, or you can put them in the chat. So as I said, the questions can be related to the talk or making a career in astrodynamics or something like that too. Because it's not something, it's a wonderful topic. I mean, I really enjoyed the talk today, but I don't think a lot of people know about this. So maybe Komal, if you can just briefly say for 2 to 3 minutes what do you think that people should do if they want to make a career in astrodynamics? Like how should they start about and all that? Any suggestions?
Well, um, to think about it, astrodynamics is not very old, but still it's kind of old because it comes from classical mechanics and orbital dynamics, like I said, and it has been around since Newton and Kepler came up with their laws of motion, laws of planetary motion as such. So it and astrodynamics, modern astrodynamics, in its true sense, only started with the beginning of the space age, which was when Russia first launched its satellite. So it's something that interest in astrodynamics is founded on interest in orbital dynamics and interest in classical mechanics. So, yeah, as to how to make a career in astrodynamics, I am not sure because even I just kind of fell into it. Without much thought. And before, our college, remember, Suri, where we had this one course called Classical Mechanics, and that was all the foundation that was the only subject in my master's of physics that has been, applicable to my in this area. So I am not sure, but you can start by, thinking about things like maybe assets in space and satellites and orbits. But I'm not sure how to answer that.
Okay.
How to,
I was just curious, like, were you actually looking for such positions, like when you applied to Canberra, or how did you know? That's what I'm trying to say. Like,
honestly, I was just looking for an interesting, project to work on, and I have always enjoyed classical mechanics.
Okay.
So I thought, yeah, this looks nice, and then it just kind of, grew into this whole world, this whole thing that I had at the end of my master's thesis. So started with for me, it just started with an interest in classical mechanics, then it went to orbital dynamics and astrodynamics, and then it went to SSA, which is astrodynamics and its applications to make, space safer for everybody, safer and more accessible to everybody. So yeah, just kind of, for me, it's something that just happened. Not sure how else to put that.
Yeah, we get it. So people, remember, even, a lot of people take classical mechanics for granted. So even classical mechanics itself is very important for a lot of stuff, not just what Komal has presented today. So do study it well. And so I think there are two people, like we have a hands up by Divyaj, and there's a question in the chat too. So Divyanshu is asking, do these debris and satellites also disturb the ground-based observations? And if yes, how do they manage it?
So ground-based observatories are affected mostly by, not directly, no. Ground-based observatories are not affected exactly by falling debris. So, for example, what is the probability that a piece of space debris will fall on your ground station? It's very low, right? So it's not something that directly affects ground-based observatories, but still, if we can't ignore the fact that there are near-Earth objects that might one day collide with the Earth, and there are things that might, damage.
I think Komal is trying to ask if they can actually obstruct the path of the electromagnetic waves or any other such things, cosmic or astrophysical messengers that reach Earth.
Oh, you mean like communication link between the ground-based
No,
observatory and
like I think the question comes from the way of thinking that if there is some infrared radiation or micro radiation from an astrophysical site and it's trying to reach the Earth, can it be abstracted by the satellite in between? Like, does it act as a shield and not letting the ground-based observatories observe properly?
Oh, no. Well, no, because if the debris was that big that we could, that it could interfere with our ground-based observatories, with the observations made by these radars and other systems, then it would have been like a win-win situation, because then we know where these debris are, right? But these are so small. These are like objects that are 10 centimeters or even less than 10 centimeters across, and they are hundreds of kilometers away from you. So no, they don't affect observations in that sense.
And in regards to that, what do you think of Starlink? So people recently, astronomers have tweeted a lot that Starlink might actually do this. Do you think it can disturb the observations?
Yeah, so these things, Starlink is a network of CubeSats, right? If I'm not wrong. So
Yeah.
it's CubeSats. So these CubeSats, the problem there is because the light reflected off these CubeSats will affect astronomical observations. And so the problem is not purely astrodynamics problem. It is a SSA problem, because the number of satellites that are planned to launch to go into orbit as part of Starlink is huge. So I'm not sure about the exact number, but I think some hundreds or thousands of satellites, thousands of CubeSats are proposed, right, for Starlink itself. So in that sense, it will only make the SSA problem worse, So it'll, even though we can catalog it, but it has, every time you put something in orbit, you're only making it worse. So yeah, it's bad in that SSA sense. Not bad, but yeah, it's something that reinforces the need for having good space tracking capabilities and good SSA infrastructure.
Yeah, makes sense. So I do have some questions to ask, but if if you all have any questions, you can click on yes.
Dwij asked, why is orbital mechanics, astrodynamics, celestial mechanics, etc. not in the same topic, and why is it so diverse? I think it's because people tend to use them in different contexts. So for example, celestial mechanics is usually something that is used by physicists for, telling for positions of planets and as such, planets and asteroids. Orbital mechanics concerns itself with smaller objects, and astrodynamics concerns itself with man-made objects. So it's not even just the difference in jargon. It's also the to some extent it's the difference in the forces that are that are acting on these objects in consideration. So for example, in celestial mechanics, you have the main force is gravity, you have third body perturbations, but you don't have things like drag, for example, things like Lorentz force, because I mean that's not something that is a problem for them, for celestial mechanics people. But for astrodynamics, since we concern ourselves with orbits around the Earth, we have to worry about Lorentz force, we have to worry about solar radiation pressure, we have to worry about what was it? We have to worry about inhomogeneous nature of the Earth. So, and on top of that, we have to worry about third body perturbations, which is something that classical mechanics people also consider. So I think the nature of the problem makes the fields very diverse, and that's why it's because the field itself is so big, it's better to just divide it into 3 different aspects and let people work in those, and rather than trying to compress everything under one umbrella. Yeah, Surendra, you were saying?
Yeah, so Komal, do you use post-Newtonian? I assume you do, right?
Sorry?
Post-Newtonian?
Post-Newtonian mechanics?
Yeah.
Not really. I don't use it personally
Okay.
because my work is more into, you know, it's just stuff that is already in place and, you know, using those. But no, my work is not based on that. But yeah, Astrodynamics does use post-Newtonian.
Yeah, because I remember reading sometime back, like since you mentioned the inhomogeneous nature of the Earth so much, so I remember actually reading a book on post-Newtonian and where the author was actually talking about this inhomogeneous nature of the Earth and its effect on the celestial
Yeah,
mechanics.
yeah.
Etc.
So like J2 harmonic
Yeah,
perturbation stuff,
yeah,
right?
yeah,
Yeah, yeah,
exactly.
yeah. We don't use that part is important. That part is actually built into the libraries and the modules that we use. So I don't have the direct dealings with those things, but
Okay.
yeah, indirectly I do use them.
So is there any open source software which, when you mention these libraries, or all this is just private?
Oh no, so there is open source stuff. For example, so there's something known as ORCID. Let me just find that.
Yeah.
Yeah, ORCID. Yeah. So this is a library that has everything that you need for to simulate a flight. For example, it's like space flight dynamics, and this is stuff that is actually used within my group. So the code uses this library pretty often, and there is other than that, I think other than that we just use Python.
Maybe you could link this in the GitHub page and also post the link in the chat, maybe.
Oh yeah, sure, I'll do that. Let me just copy this here. And, yeah.
Okay.
So
And the next thing I wanted to ask is, do people actually conduct simulations of these collisions and see how much debris it would have produced and how much we have observed? So basically, you were trying to show two examples, right? One in 2009 and one in 2000.
yeah, this one.
Yeah, exactly. So here you showed this red thing and you said that's all which is greater than 10 centimeters, right?
Yes.
So do people actually simulate? Is it even needed to see like the collision?
Yeah. Because see, like I said, there is any object that is below 10 centimeters cannot directly be tracked. It cannot be observed by our ground-based radars, right?
Yeah.
So we need simulations as a statistical model to tell us how many potentially lethal, and by potentially lethal I mean anything that is bigger than 1 centimeter across. So these simulations help us to statistically model those debris pieces that we cannot directly observe.
And they validate the simulation models by actually comparing the one which we can actually observe, right?
Yeah. I think that's something that must go on, although I'm not sure how that would work. But yeah, I think that is something that the validation part is done before the model itself is deployed. So it's tested, it's validated, it's once you're sure that everything in it does well, then you start with the modeling, with the debris modeling. But it's mostly a statistical model that tells you how many debris in what size will be generated.
Nice. This is really interesting. And you were also saying that you recently attended some talks on space debris cleaning, and you were saying that some people try to propose lasers to push out larger objects, but any ideas on the smaller objects which
so no, I didn't want to include it in my presentation because that was a talk that I attended last year.
Okay.
That was in July or August last year. And that was a bunch of people were here in Canberra, they were trying to discuss the threat of orbital debris, and they did propose some crazy ideas that they did mention some crazy ideas or seemingly crazy ideas that other people have proposed. So yeah, one of those that stuck with me was this one, that we can use powerful lasers to push on debris object and move them out of the way. But that is again something that is entirely, brainstorm and entirely in the thinking stage. It's not something that has been applied.
Okay. And the last two questions maybe, so when you launch a spacecraft, I understand that if it's a big satellite, one can actually maneuver it if it has a propulsion system. But supposing there is some old debris which was not tracked properly, and this spacecraft might actually crash into it, nothing would happen to the spacecraft because it has all the shielding and etc. But that would produce more debris, right? And that in itself will again cause more problems to the other things that are orbiting. So how do they try to take care of this, that the space shuttle doesn't actually crash into so many things, not the big ones, but the small ones, if at all?
So yeah, the debris has in fact caused problems for different missions, and space shuttle windows, for example, have had to be replaced because of debris. Yeah, so before the mission is planned, prepared, launched, they do see like this is part of the orbital prediction prediction algorithm, that they would know where if there is a threat to space debris, if it is from something that is in the catalog and can be predicted. But if it is with something that is smaller, or then yeah, there's nothing that we can do right now. Yeah. And there is interestingly, there is a theoretical scenario that was proposed in 1978, I think, but yeah, late 1970s, that where the density of objects in orbit is so high that it essentially creates a cascading sort of effect, and so each collision will create more debris, and then those debris fragments will contribute more collisions and more debris, and then it just increases exponentially, and it's called Kessler Syndrome. Somebody must have heard of it. So yeah, it's a theoretical scenario that is pretty scary, because the end result of such a scenario where such a cascading effect has occurred is that the orbit becomes entirely unusable, which means that there are the density of debris objects is so much that you cannot launch into that orbit at all. So it renders the orbit entirely useless. And it's a pretty scary scenario, which is why SAYs become even more important in these days, so to prevent something like that.
So is there a prediction system to actually look at this tipping point when the cascade happens? Like, do people try to take care of that too, or no?
Try to take care of what exactly?
The tipping point as to when this cascade might actually happen.
Yeah.
Like, is there any what you call some prediction which
Threshold?
can? Yeah. Threshold. Yeah.
Oh, so I'm not sure if there's a number that if the number of debris is larger than this number, then the Kessler syndrome has actually happened. I'm not sure if there is one, but it's just a theoretical scenario that basically says the cascading effect is here, and the avalanche is here, and it has rendered your orbits unusable. So I think when it happens, we'll know, but I'm not sure if there is a theoretical scenario that there is a threshold number that predicts it.
Okay. So Divyanshu here has a question. Considering the low orbit, the number of debris is very large. how do they deal with in order to keep ISS safe? With strong sheets or anything else?
Yeah, so one thing that is done is shielding. Obviously, shielding is a really important part of space missions, and in fact, material science is contributing a lot to it, because we need materials that are, that can be used in those circumstances, and that can prevent, that can stop stop the debris fragments. For example, there is research in aerosols, which is supposed to like catch or like a sponge, it's supposed to just catch the debris and prevent it from causing much damage. And right now, the way that they deal with it is that they predict the collision, try to predict if there is a collision that is imminent, and then they just move out of its way. That's all. So yes, shielding is one part, and maneuvering is another part. Now, I hope that answers your question.
And yeah, Komal, so you were mentioning about these ground-based observatories which try to track these different objects and get all the data on the positions, velocities, etc., right? So similarly, can there be some satellites launched in the space so that they do a similar job and may be able to track the objects which can't be observed from here on Earth, like the one which is below 10 centimeters or 1 centimeter or something?
Certainly is an interesting idea, but I don't know. If we think about it, you can put a satellite where you know that the debris will be a lot, right? So wherever you know that, okay, there is a huge risk of collision, and you can, I guess, place your satellite in that region, right?
But one can also do orbital maneuvers, shift it orbits. It's like, I'm trying to say, it's like a probe wherein instead of probing a Mars or something, it can just probe what's happening in that belt, something like that.
Yeah, but the problem remains that once you observe a debris, so for example, such a satellite won't be able to, well, let's say you launch a constellation of satellites. First thing you're doing is you have already increased the number of debris in space, right? So that's one negative thing that has already come out just simply by launching your constellation. Then once you do launch it, let's say it does observe a piece of space debris and it tries to catalog it. But then space debris is something that is not exactly predictable, because these are very, very small things that are moving at a very, very fast speed. So I'm not sure how that would work out.
Can't we at least get good statistics?
Sorry?
Some good statistics rather than having to precisely say, maybe some statistics would also help, right?
Yeah, I think that might work, but I'm not sure how that would be, implemented, because yeah, I'm not sure how such a mission would benefit. I mean, you can get accurate data, and that can help us track those less than 10 centimeter across debris that we cannot track from ground. But once again, that because of the sheer number of such objects is so large that it's very difficult to track each and every one. Even if we cannot really keep our eyes on all of them, because just to give you this one number I have here, there are more than 900,000 debris pieces greater than 1 centimeters, and this is data according to 1 January 2019. So 900,000 pieces of debris that are potentially lethal, and yeah, so it's the sheer number is so big that at that point you might as well just shield your spacecraft and hope for the best.
But yeah, I was thinking more in terms of statistics rather than trying to get an accurate number. But yeah, maybe there's some paper which actually does this cost estimation, not in just financial terms, but also in terms of debris, etc. Yeah.
Yeah, we can model, we have ways of modeling, statistically modeling the number of debris.
Okay.
Like even from ground stations, even with the current technology, we have statistical models that tell us, okay, this many debris pieces are present in between these altitudes. So yeah, we already have that.
So any more questions, guys? Okay, if not, so Komal will be putting up the slides on the GitHub page, so do keep an eye out for it. And I also requested her to put the link to the software that she generally uses. Okay, there's one last question maybe we can take, and with that we'll stop. So Divyanshu is asking, these debris are mostly metallic in nature. A huge magnetic satellite with a surface of aerosols you mentioned, can it do the job of, I think he's trying to ask cleaning the debris.
Again, this is something that we can think of. Let's say you have, first of all, yeah, to answer the first question, there are debris pieces that are metallic, but there is also stuff like glass, fragments of solar panels, plastic, anything that the satellite is built of, to be honest. And there are rocket bodies and stuff like that, which is bigger, but for the smaller debris, then yeah, there are even things like paint flecks of paint that have somehow gotten off of your satellite, or during whatever launch or whatever. Even these things are they can cause damage to your assets. So yeah, they are metallic in nature, but there are also other substances. Everything that a satellite is built of, you can expect to find it up there. And a huge magnetic satellite with the surface of aerosols you mentioned, can it do the job? I think theoretically you can put something that has a magnet and aerosols on it, and then it can go around cleaning the area. But this may present other problems such that, how do you build such a satellite? How do you launch it? How long will it stay there? What material is it going to be? Would it accidentally create more debris? For example, if something big collided with if it's a huge satellite and something big collided with it, does it have a risk of creating more debris while trying to remove the existing debris? So these things have to be considered, before. But yeah, interesting idea. I think definitely has some merit, but I'm not sure exactly how this would work in practice.
So Komal, is there an organization called SSA or any other? What's the major organization which takes care of these?
So there are organizations that track and catalog space debris and other objects. So for example, NASA does a lot of does a lot of catalog managing. The United States Air Force does a lot of tracking and surveillance. And there is a space surveillance network, which is part of the United States military, I think, or Air Force. But yeah, there are organizations that individually keep track of debris, and the aim is to share data, and then to share data and to share the knowledge that we have. But multiple organizations do it.
So there is no one such organization which actually leads this kind of thing, or is there?
Leads. Well, I think NASA can be called a leader. In terms of number of objects tracked, United States Air Force is the leader.
Okay.
Yeah, and in terms of the one that manages the catalog, NASA will be the leader, NASA and NORAD. Yeah, so they would do it. ESA is also a big player, European Space Agency. Yeah, so these people kind of collaborate to make sure that a catalog is maintained and kept up to date. Yeah, there is one question here. Can you shed some light on space debris removal using lasers? I can't, because that's just something that I remember from this lecture I attended last year. But I am not sure how it would work. And yeah, the reason why I remember it is because I'm not sure how it would work, and it has kind of stuck with me over the year. But yeah,
Maybe,
I think
Komal, if you can try to find a link to that presentation or talk or something and put it
I
in.
will try to find it. Yeah.
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 So
I'll try
guys,
to find it and put it there.
yep. With that, I think we can conclude our session today. And as I said, the talk will be uploaded on a YouTube later, and which will be shared with you. And Komal will be uploading the slides with a few minor changes that we suggested along the talk and uploaded the GitHub page. And if you have any questions, you can always email her, and she has provided the email in the GitHub page. And with that, I think, Komal, thank you very much for today's session. I found it really interesting personally, and I think it's the same with everyone else. I think everyone else also found it very interesting. And yeah, I never imagined that this was such a serious problem, space awareness. And yeah, people are saying it was great in the chat.
Thank you. Thank you so much.